On these power series, the trend that you're going to see is that in all power series, you're always going to have this progressively higher power of x as you move through the series. The only real thing that changes in a power series are the numbers in front. Those are the only things that can actually vary, are the numbers. Other than that, they all have a similar kind of look to them. So I'd like for us to take a look at this power series. It's the power series where I'm actually going to give you a formula. And I should go back and write this down because I forgot to point something out. That was the formula for the power series. This C sub n, bless you, this C sub n, that right there is our constant, right? Yes? This right here, I want you to visualize that as being the A sub n from the series we've been looking at. Remember how we've been doing series and it's always been series A sub n, right? And this was just, this number, whatever came out here was just controlled by the n. Whatever n was would determine this piece. Well, this piece right here is controlled by n. So as you plug n in, this is going to change just like the A sub n's changed. What we've tacked onto these things now is in addition to some constant that is changing, we've tacked on powers of x. All right? So we've included this new variable in here. All right, so here's your first example. I'm going to give you a formula for the C sub n, and here it is. It's very complicated. You ready? It's going to blow your mind. There it is. C sub n is 1. This is like the most generic, boring power series that you can look at, really. Because what I'm telling you is that the constants in front of each of the x's is always 1. All right? So they're not changing. So what would this look like? What would C sub 0 plus C sub 1 x plus C sub 2 x squared plus C sub 3 x cubed plus dot, dot, dot. What would that actually look like? That would be 1 plus x squared plus x cubed plus x to the 4th plus dot, dot, dot forever, right? So this is a generic power series. Here's the power series for this specific example. Got it? Now, written out in sigma notation would be C sub n times x to the n, right? But what's C sub n? 1, so it's just x to the n, isn't it? Anybody recognize that series? Drum roll. Anybody recognize that series? Put these ones back in here. P, okay, that I had in my other class, I had a good student tell me the same exact thing. P series. Close. If you look back on P series, and this is a common thing to flip around. On P series, we had n to the p. So the base was being controlled by the n, and the power was fixed. Here, the power is changing, and the base is fixed. Geometric series. This is a geometric series. Now look, I'll try and help illustrate the geometric series just underneath it. Doesn't this look like a plus ar plus ar squared plus ar cubed plus ar to the 4th plus dot, dot, dot? Wasn't that geometric? To the what? Plus. I'm lost. What?
See how like to the left, you have 1 plus 1x plus 1x squared. So where's the plus 1 in that sum?
Where's the?
Because you have x is 0.
You're okay? Okay. All right. See the geometric? What's A? 1. What's R? X. Right? So this right here is basically a geometric series with A being 1 and R is actually a variable right now instead of a nice fixed number. R is x. So can you tell me when this will converge? Exactly. So let's say that with absolute values. This will converge. Converges when? If the absolute value of x is less than 1, right? Which really means that x is between -1 and 1, right? Do you agree? So every time I've given you a geometric series in the past, right? The r was a number, wasn't it? This time, with this particular power series, all you can say is this. If x is kind of like a variable, then the only way that this power series will converge to something is as long as the x that you want me to plug in is bounded between -1 and 1. If it is between -1 and 1, this thing makes sense. What if the x is outside of this? It diverges, and that sum doesn't make sense anymore. Let's go back. Let me say that again. You mean to tell me that I've given you something here, right? I've presented something to you. I've just placed it right there in front of your face. There it is. And for certain values of x, this sum makes sense and goes to a number. But for other values of x, it doesn't. Right? Kind of like when I put up here that, and I said, what's the domain? And everyone said, oh, well, the domain of this is anything bigger than 0, right, including 0. And I tried to get you to understand that what that means is that if I plug in certain values of x, this makes sense, but other values of x, it doesn't make sense, right? So what do you think I'm about to do with this? I want to talk about domain, right? But if I'm going to talk about domain, I better actually call it a function. I now am going to define this to be a function. F of x equals this infinite polynomial. Now, this infinite polynomial that I'm about to define has a domain. For certain values of x, it makes sense. For other values of x, it doesn't make sense. So are you buying into the idea that I'm actually going to be able to define a function that actually never stops? Like, it's an infinite sum, but I'm going to define it. And this is where I was trying to explain to you that in chapter 8, the whole point is to try and take a function like sine x and be able to rewrite it in its infinite polynomial. And then we can integrate it, differentiate it, and do everything we want to do with it calculus-wise. All right? So we're actually going to be doing the reverse of this later. I start with a function, we turn it into its power series. But we got to start with the power series, all right? This is amazing that this actually works this way, but it does. All right, so now let me define if we define f of x to be equal to c sub 0 plus c sub 1x plus c sub 2x squared plus ... right, which equals sum n equals 0 to infinity. I've moved away from that example, okay? I'm done with that example for now. I will come back in just a moment and address it. I'm just going to pick up with the general idea here. If we define a function to be this infinite polynomial, which is a general power series, then the domain of f are the values of x for which the series, what? Converges. So going back to the example, if I define this to be f of x, define this to be f of x, the domain of this is negative 1 to 1, right? Negative 1 to 1. So you might be asking yourself, wait a minute. If this is a function, I should be able to graph it, right? Like, if I ask you to graph square root of x, you could graph that, right? So you should be able to graph this. You think you can? Let's try it. Let me ask you, for this function, what's f of a half? Okay, so that would be 1 plus a half plus a fourth plus an eighth, blah, blah, blah. But remember what this series right here, this specific example I just gave us was a geometric series, right? That geometric was only if these c's were always 1s, right? In this particular case, this is a geometric, a being 1 and r being x, right?
2.
So it should be 2. How'd you get 2?
1 over 1
Yeah,
minus a half.
a over 1 minus r, right? The formula for a geometric series is that as long as the absolute value of the x is less than 1, it'll converge to a over 1 minus r. So if the x that I'm plugging in, which is really r, is 1/2, that is less than 1 because it's in our domain, right? Or the absolute value is less than 1, then it's going to spit out 1 over 1 minus a half, which is going to be 2. Okay, good. What's f of negative 1/2? Well, that's in the domain, right? So what would that give you? 1 over 1 minus negative 1/2, which should be 1 over 3/2, which is 2/3, right? Man, this is like x coordinate, y coordinate, x coordinate, y coordinate, right? Input, output, input, output. How about I try and trick you? What's f of 0? 1. Now, why didn't you use the formula? Because if you try this formula, 1 over 1 minus, oh wait, this one does? It does work, right? But 0 in here, what would 0 in here for all your x's give you? Just 1, right? Why did I try that? Oh, I'm thinking about something else, sorry. This is 1, right? We could graph it. Wonder what the graph looks like. Well, I had my computer do it, okay, because I didn't feel like doing it. So here's the graph. That's not the graph. That's the graph. Let me make this a little bigger. That is the graph of the geometric series 1 plus x squared plus x cubed forever. You plug in an x, it's going to spit out a y, and here's the plot of it. Now it stops at 1, right? And negative 1? You can't plug in 1, you can't plug in negative 1. There's your domain restriction. Pretty cool, huh? Yeah, that's awesome. Maybe it'll help if I remind you of something here. Take a look at that curve, that red curve. Can you all see it okay? Now ignore this vertical line because that's an asymptote. My computer's having a problem with that, so it's drawing a vertical line. All right, so right now I'm going to try and approximate that curve. I'm going to try and create that curve. Do you remember me doing this before? Now it's going to make a little more sense. So I'm going to start Do you see my approximations in there? They're actually pretty good. Let me back up. I went too quick. Okay, there was my first approximation. Now the function is x to the fifth over 2 plus x. I approximated it with x to the fifth, and it was decent. Then I went out a little bit more. Now I'm approximating it with x to the fifth over 2 minus x to the sixth over 4. And do you see the black one there? It's better, but see, it falls apart over here on this end, doesn't it? But I'm going to go further out, and I'm going to start approximating. Look at how this thing marches its way closer and closer to the true answer, right? But what have I created up here? I know it's hard to see from where you're sitting, but do you see that this is a polynomial? Do you see this polynomial? Yes? X to these powers. Look at the powers. Fifth power, 6th, 7th, 8th, 9th. So this is a power series, isn't it? The only thing that's different is the numbers in front. This number, the number that's in front of this one is 1/2. What's the number in front of the next one? Negative 1/4. Next one? 1/8. Negative 1/16. Ooh, there's a pattern there. Right? I think we might even be able to generate the formula for that. So our goal later is this. I give you function, you give me power series. I give you function, you give me power series. And the value of this is, well, that's the way a computer looks at a function. It doesn't look at it this way. Well, this function's kind of generic, but if we go to like exponential or logarithms, like I think I had a log function in here somewhere. Was it at the bottom? There we go. There's a log function. Let me pull this off. Okay, so you can see I'm trying to approximate this log function. I start approximating it with a line, and then my line's going to become a parabola, and I'm starting to curve this thing, and see it starting to converge to the function. So it turns out that every function out there, pretty much, you can convert it to its power series. And that's what Newton was able to do. That was so awesome. All right. You're as thrilled as I think I'm going to get you to be. All right, so now we have a little bit, we're going to just shift a little bit the gears here. I want you to remember that when we had functions like, let's take that root one again, that if I were to say, look at that function, but instead of root x, do root x minus 4, what's the difference in these pictures? This is shifted to the right 4, right? If this was a plus, left 4, right? So if I were to write like that, that would be to the right by a. If a was positive, right? This would go to the right a. If a was negative, it would go to the left. So I'm now going to change our definition on purpose. So we kind of waited before we gave you this. The general power series formula. And this is a power series. We call this a power series about A. The power series about A. All that about A means is that we're going to shift the power series around. We want to be able to slide this function left and right. So here's what it looks like. It's c sub 0 plus c sub 1, but instead of x to the first power, x minus a, plus c sub 2